In this video, we learned to visualize position and velocity for an object moving in one dimension, and we established the meaning of slope for a position time graph and the meaning of area for a velocity time graph. So we begin with an example, and in this example, we're told that a car starts at the origin and drives 90 miles to the north at a constant rate in 2 hours. After this, the car turns around and drives to the south 90 miles at a constant rate in 3 hours. We want to plot the position of the car as a function of time. And for this, we use a position time graph. On this graph, the vertical axis tells us the position of the car relative to the origin, and the horizontal axis tells us the time. So each ordered pair gives us a moment in time together with a position in space, and this is how we describe the motion of an object moving in a straight line. The natural units for this problem are miles for the position and hours for time, and we start plotting some points on the graph. First, when the time is equal to 0, the car is sitting at the origin. That's an ordered pair, 0, 0. Next, we know that when t is equal to 2 hours, the car is 90 miles north of the origin, or 90 miles in the positive direction. And the scale on this graph is 10 miles for every grid space in the vertical direction. So just as an intermediate point, 50 miles is right there, 5 grid spaces up. And 90 miles is 9 grid spaces up on the vertical axis. And our grid spacing is 1 hour per space on the horizontal axis. And so a time of 2 hours is 2 grid spaces to the right of the origin. So when we get to t equals 2 hours, x is equal to 90 miles, and we get our second point on the graph. Again, that's an ordered pair with the time coordinate coming first, that's 2 hours, and the position coordinate coming second, that's 90 miles. Finally, we know that when t is equal to 5 hours, so that's 3 hours later, the car is back at the origin. It's moved 90 miles back to the south, and it's where it began. And that's an ordered pair of 5 hours, 0 miles. And because these motions occur at a constant rate, we can connect these points with straight lines to obtain the position time graph for the motion of the car. Next, we start to think, what does the slope mean on this graph? And there are 2 different legs of the journey to analyze. In the first leg of the journey, as the car moves 90 miles to the north in 2 hours, we can compute the rise for that. In other words, the vertical change on the graph, and that's plus 90 miles. And we compute the run for that. In other words, the horizontal change on that leg of the journey, and that's plus 2 hours. And then, of course, the slope is given by the rise over run, and we're careful to keep the units on this because it has a physical interpretation. That's 90 miles over 2 hours. And I end up with a positive 45 miles per hour. And I'm going to go ahead and write the plus sign out in front because that's indicating the direction that the car was moving. I get a positive slope on the position time graph because the car was moving to the north. So this is telling us a velocity for the car, in other words, a speed and a direction. And in fact, it's an average velocity on this leg of the journey. If we started this over and I asked, what's the average speed of a car moving 90 miles in 2 hours? Of course, we would say it's 45 miles per hour. And then the plus sign gives the northward direction here, so it's a velocity. So as the car works its way back to the original position, I'm going to call that a rise of negative 90. So I started at 90 and ended at 0. And the run for that was plus 3 hours. And again, we're careful to keep units on the rise and the run because they matter. And I end up with negative 30 miles per hour. And again, when we think about a car moving 90 miles in 3 hours, of course we think that's an average speed of 30 miles per hour. And then the minus sign there gives you the direction. So this is a velocity. And this gives us our first major conclusion of the video. And this is worth remembering, so I'll put it in a box. The slope between 2 points on an xt graph gives us the average velocity. Next, we consider a velocity time graph for the same example. A velocity time graph tells us the velocity of an object as a function of time for some object moving in one dimension. Well, we know the car moves positive 45 miles an hour for 2 hours, and then negative 30 miles per hour for 3 hours. So we plot these constant velocity segments as horizontal lines on the VT graph like this. I'm calling each vertical grid space 10 miles an hour here. So 45 is right about here. And that's constant for 2 hours. In other words, we stay at exactly the same velocity value as t goes from 0 to 2, and that gives me a horizontal line. Then the car turns around and takes a negative velocity value. That's negative 30 miles per hour. That starts at t equals 2 and goes all the way to t equals 5. And it might be nice to connect those with a dotted line. Next, we're asked to interpret the signed area bounded by the graph. In other words, the area bounded with respect to the t-axis where it's considered negative if the function is below the axis and positive if it's above. All right, these areas are just rectangles, and I'll just label them as A1 and A2 for the different parts of the journey. And then we'll calculate the area A1. And you just take the width of this thing and multiply by the height, but we're going to keep the units on it. So the width for A1 is just 2 hours. And I multiply that by the height, which was 45 miles per hour. And the hours are going to cancel out of those units, and I get 90 miles. Well, what's the physical interpretation of that? That's the actual displacement of the car during that first leg of the journey. It moved 90 miles to the north. We do the same thing for A2. That area has a width of 3 hours. And then we'll take care to keep the minus sign on the velocity here. So the height of that rectangle is 30 miles per hour, but it takes a minus sign because it's a negative velocity, or I could say because the graph is below the t-axis. The hours cancel, and I end up with a negative 90 miles. And again, I'm looking at the displacement of the car on that time interval. It went 90 miles to the south. And this gives us our second big conclusion of this video. And this is a big deal, so it also gets a box. The signed area bounded by a velocity time graph, that gives you the displacement for an object. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.